Hello, good morning. Am I audible?
Yes.
I hope you can see my screen. Is it visible? Display का screen.
Yes, sir.
Okay, thank you. काय कशी गेली दिवाळी? उमेश, ओंकार, आकांक्षा, मयूर. How was your Diwali? Pallavi. Say something. Sanchit. Pranjal. So yesterday we were talking about state feedback control. So state feedback control is designing the K x dot is equal to ax plus bu, y is equal to cx. And if we represent this in the form of block diagram, I can write it like this. So here it will be A matrix x, x dot, here it is B, here it is C, here it is Y. All right. So this is a state space representation or state flow diagram. And our objective is to design U is equal to minus kx. So with that, we put minus k over here and we connect it so that we will have state feedback controller here, state feedback controller. So with this, our system becomes closed loop system. And for that, we have seen three methods like direct, substitution, matrix transformation, and Ackermann's formula. These three methods we have seen. And we have seen a numerical also with all these three methods. All the methods are very simple. Some steps we need to follow. And if we follow those steps correctly, we will get the answer for K. Answer obtained by all the three methods is same. provided our desired eigenvalues are same. So this is what we have done in last few lectures. Now, the main problem is that here we are giving a feedback. हा इथे आपण एक feedback देतो. Let us consider the example of DC motor. If I consider the example of DC motor, this X will be your armature current and speed. So here I am having like two outputs or two states coming out of this. One is your current, one is your omega, right? And then suppose these are merged together and we get only one state vector which is given to K over here. इथे K ला आपण दिला तो, इथे K ला तो जोडला. Okay. So here we need to note down one important point is that here the dimension of X is n by 1. n by 1 म्हणजे इथे किती आहे 2 by 1. And here the dimension is 1 by n. 1 by n. म्हणजेच काय u is equal to minus kx. K ची dimension काय 1 by n आणि x ची dimension n by 1. So we get 1 by 1. Answer is 1. Suppose we get one input here. We get one input here, which is given to P. Okay. म्हणजे जेवढ्या x च्या टर्म्स राहतील, जेवढे x चे स्टेट व्हेरिएबल्स राहतील, तेवढ्या तुमचे k चे व्हॅल्यूज पाहिजे इथे अशा 1 2 बरोबर ना. So that you can multiply and you can get answer as 1 by 1. Now thing is that here I am taking this feedback. इथे मी हा feedback घेतोय. I am taking feedback of current omega. I am taking this feedback means I am measuring the value of current and I am measuring the value of omega. And then I am giving it to the feedback. Now this part will be implemented in computer. This part will be implemented in the computer. So I am taking the feedback. I am taking the values of armature current and omega from the actual machine and giving it to the computer where these two variables are multiplied with the gain K, and then it is going out of the computer which is given to the system again in the form of voltage. Now this is voltage applied as voltage to the system. Are you getting my point? समजते का तुम्हाला मी काय सांगतोय ते? If you are not understanding, I will repeat this. Are you getting my point? Type yes or no in the chat box so that I can understand. Hello?
Yes, sir, understood.
Okay. So what I am doing is I am taking the feedback, I am taking the value of current and omega from here and it is given to the computer here and then it is done. Now, sometimes in a system, there are some variables. आता इथे हा current जो आहे, this current can be measured with the help of ammeter, or this speed can be measured with the tachometer, and that reading can be given to the computer. But there are some variables in some kinds of systems where we cannot measure them. We cannot measure those variables. Right? So, or sometimes we do not have any instrument to measure them. Or sometimes it is very difficult to put sensor for that, or it is very expensive to put some sensor over there. आता ह्या सगळ्या व्हॅल्यूज ज्या मोजायच्या त्या सेन्सरनी किंवा मीटरनीच मोजायचे. इथे अॅमीटर वापरला, इथे टॅकोमीटर वापरला. So sometimes in some physical systems like chemical processes, suppose we want to measure the concentration of some other element. So in that case, we do not have any exact measurement device to measure the concentration of that particular component. So it is not possible to give the feedback. जर समजा इथे मेजर करण्यासाठीच काही नाही, सपोज वी से दॅट वी डू नॉट हॅव एनी इन्स्ट्रुमेंट टू मेजर द स्पीड. मग स्पीड मेजर करण्यासाठी जर इन्स्ट्रुमेंटच नसेल तर इथे काय द्यायचं मग? व्हॉट वी शुड गिव्ह हियर? ओनली वी कॅन मेजर करंट, but we need both the values so that we can multiply it with the k and then we can get v. But suppose one variable is not available for the measurement, or for that sensor is not available, or for that sensor is very expensive, so we cannot measure that. So in that case we need to estimate that value. We need to determine that value by some calculations. We need to observe that value, and that is called as the observer. That is called as the observer. So we have to mathematically determine that value and then we have to feed it to the k. That means here this k will have some values measured from the system actually and some values measured from the or calculated from the calculations, obtained from the calculations. So we are giving speed directly from the tachometer and current we are calculating. So this calculated current is called as observed current, and for that we need observer. For that we need observer. So this is the concept of observer. I will show you it in more detail. Okay, I hope this presentation is visible to you. Okay, now here I am just giving a small presentation on full order observer and reduced order observer. Actually, in our curriculum, we do not have this reduced order observer. We have only full order observer. So we will discuss only that part, and rest we will not discuss. So here you can see this is a process system, DC motor suppose, and here we are getting some outputs, but some of the outputs are not measurable. We cannot measure them. So we observe them or we estimate them and then we give it to the controller, and then controller is given to the system. This is what is shown over here. I can show you here. So this is our general system. Here I am using Z instead of X. So dz by dt or z dot is equal to az plus bu, y is equal to cz. This is our standard system that we have shown over here. He ji system दाखवलेली आहे. This is the same system shown over there. Only z is used instead of x. Z is used instead of x. So z dot is equal to az plus bu, y is equal to cz, where the dimensions of z, u, and y are given. Matrices A, B, C are of suitable dimensions. Let the feedback control. Now this control feedback is U of t is equal to minus kz. U of t is equal to minus kz, and k is the feedback gain matrix. Now here dimension of k is m by n, whereas I have written here dimension as 1 by n. This 1 indicates input. 1 indicates input. Here we are assuming that only one input is there. But in practice, there can be m number of inputs. That's why here m is appearing. This m. So U of t is equal to minus kz. Then our system can be represented in the MATLAB like this. This is what I have shown over here. इथे पण तुम्हाला मी दाखवलं आहे. This system is shown over here. Each system मी तुम्हाला इथे काढून दाखवलेली आहे. So here we have states are given to A, AX. Here I am coming BU. So AX plus BU, X dot, integration and X. Output is given as CX. And here this is state feedback control, minus K, and here it is given. हा red जो box आहे, that is your system. आणि हा जो खालचा जो blocks आहे, this is your controller. Right? Now, problem is that, as I said, large scale systems with the full state feedback have many feedback loops. जर का system आपण आता 2 by 2 consider केली, त्याच्यामध्ये current and omega, only 2 states variables are there, but there are physical systems where many variables are available. Like hundreds of state variables are available. And in that case, it is not possible to measure each variable. Some variables we have to estimate by estimator. Some variables we have to estimate by the estimator. So often all the states are not available for the feedback. Here you can see. States are not available for the feedback or the measurement. Like as I said, current we can measure by the ammeter, speed we can measure by tachometer, but there are some variables where we cannot measure with any other instrument or measuring device. So in that case, it becomes very costly or impractical to measure the that variable by the sensor, like precursor concentration measurement in the nuclear reactor or velocity measurement using gyros in the space vehicle. So we cannot measure them, but we need those variables for the feedback because we are implementing state feedback control. आपल्याला ते पाहिजेत, but we are not able to measure them, right? And for that we go for the estimator. For that we go for the estimator. Now what is estimator? Estimator or the observer. This is actually developed by Leuenberger, observing the states of the linear system. This was the paper written by him, David Leuenberger, and you can see that he was a student member of IEEE, and that time he developed this Leuenberger observer, and it is widely used in control applications. This is one of the biggest development in control theory where observers are used. Because of that, we are able to estimate many states, and these states can be given directly to the controller, where it provides the same response as that of the actual system. म्हणजे you will be surprised to know that we can mathematically calculate what value will the speed have after 10 seconds, and that value is given to the controller, and the controller produce the same kind of output as if the actual value of speed is given to it. So this is one of the biggest contribution in the control theory, development of Leuenberger observers, and these observers are often called as Leuenberger observers. So what is observer? Observation is what? Estimation of the unmeasured state variables using y and u. So we for any system, what do we have? For any system, we have, for any system, if I draw a system here, for any system, we know what input we are giving and what output we are getting. We know what input we are giving and what output we are getting, that we know. But sometimes we do not know the states. Sometimes we do not know the states. So input is known, output is known. So with that, we estimate the states. Observer. We take input from the states, we take input from the output, and we estimate the states. We estimate the states. So estimation of the unmeasured state variables using y and u. State observer, a device, it can be electronic component, hardware, or the equivalent computer program that estimates or observes the state variable is called as the state observer or simply observer. It is called as state observer or simply observer. Full order observer is where we estimate all the states, like if we are estimating both. In case of DC motor, we are having two states, armature current and omega m, speed. So if we are estimating both IA and omega m, then it is called as full order observer. We are estimating all the states. It is called as full order observers. And if we are estimating fewer states than the actual states, then it is called as reduced order observer. Reduced order observer, it estimates states fewer than n. So maybe if I'm estimating only omega, then it is a reduced order observer. Or if I'm estimating only IA, then it is reduced order observer. And minimum order state observer is that if the order of the observer is minimum possible, then it is called as minimum order observer. कमीत कमी किती states आपण observe करतोय, that is minimum order observer. Okay, so this is what I have shown earlier. This is my system. This is my observer. Observer is taking input from the U and output, and it is estimating the states, and then it is given to the controller. Then it is given to the controller. Have you understood this? किती लोकांना समजले ते? Reply yes or no. किती लोकांना समजलंय, किती लोकांना नाही समजलंय? I can repeat this. Okay, okay. So our system. So our system is this one. Let me draw it once again here. This is U, C, Y, X. This is our system. And here we have K. इथे आपला K आहे. This is X dot. This is X. Problem is that we cannot use direct X from here because we do not have any instrument to measure it. Right? So हा K ते इकडे द्यायचा आहे आपल्याला. हा K U लाच द्यायचा आहे. परंतु हा K ला जे इनपुट द्यायचं आहे ते आपल्याला ऑब्झर्वर कडून द्यायचं आहे. That input we have to do from the observer, where observer is taking input from the states and it is taking input from the Y, and then it is giving output to the X. So this kind of system we are implementing. This is observer. Why we are doing this? Because all the states are not available for the measurement. Not available for the measurement. Okay. So here we need to represent this mathematically now. It is little bit difficult to understand, but very few equations are there, 4 or 5 equations. And once you understand those equations, then there is no problem. So just try to be with me when I'm explaining to you. If at any point there is confusion, you can just ask me, unmute yourself, or you can type in the chat box. I can explain you once again. So this is our standard system that we have. X dot is equal to AX plus BU and Y is equal to CX. This is our standard system, where Y is equal to, where Y is the output which is available for the measurement, and some of the states are not available. So observer for the system can be given as Z cap dot. Now this Z cap is nothing but estimated value. Estimate केलेली value. Z cap जे आपण estimate करणार आहोत. Z cap dot is equal to AZ cap plus BU. Y cap is equal to CZ cap. Right. So Z cap and Y cap are estimated states and output. Now, when I say estimated value and the actual value, जर का समजा आपण स्पीडची व्हॅल्यू इस्टिमेट करणार असू 10 सेकंदानंतर किंवा 10 मिनिटानंतर, तर ऍक्च्युअल व्हॅल्यू पण त्यावेळेसची सेम असेल तर आपण म्हणू की एस्टिमेटर इज ऑपरेटिंग परफेक्टली. सो वी नीड टू एन्श्योर दॅट द एस्टिमेटेड व्हॅल्यू which is here estimated value should be equal to the actual value, then we can get error which is 0. He error 0 झाली पाहिजे, then we can say the observer is operating perfectly. So y minus y cap, actual value minus estimated value, is equal to cz minus c cap, sorry, cz minus cz cap. It is equal to c e of t. What is e of t? E of t is the estimation error. This error has to go to 0, so that we can say that observer is perfect. Now observer that takes into account the feedback information. Now once observer is designed, we need to take the feedback. So observer that takes into account takes into account feedback information about the observation error is given. So this is we write here the feedback or the observer gain in our system here. This is feedback gain. Feedback gain. Likewise, for the observer, there is L, observer gain. Observer gain. Like state feedback gain, there is observer gain for the observer system. So AZ cap plus BU plus L, this is estimation error, which is going to be 0 as t tends to infinity. So AZ cap plus BU plus CL, LC E of t, where L represents the observation gain. From 5 and 6, what we can get is estimation error is A minus LC E of t. When I say estimation error should go to 0, estimation error should go to 0. That means something like this, estimation error should go to 0. This is E of t. And what is E of t? Y minus Y cap. The actual value minus estimated value should go to 0. Then only we can say that system is effectively observing the value or calculating the value. And if it is not going to 0, then probably observer is not working properly. If it is not going to 0, if it is increasing, then observer is not working perfectly. So this anyway this is going to be 0 for stable system. System is stable. If A is stable, anyway it is going to be 0. But if A is not stable, then it will go to or it will go on increasing. It will go on increasing, and for that we need to make this stable. So we write A minus LC here. A minus LC. For that we design L. For that we design L by the same procedure as that we have used for state feedback control design. A minus LC. So once this is done, then your observation error will always go to 0. Your observation error will always go to 0. So this is E dot is equal to A minus LC E of t. So this L is observer gain. L is observer gain, and it is selected such that lambda A minus LC is equal to desired eigenvalues. Then the estimation error will decay to 0 for any initial condition. So this is the overall system. This is the complete system with the observer. Here you can see that. Here I was showing you. This is the existing system that we have. Okay. This is the controller that we have, and this is the observer system. So this is shown here with the help of MATLAB block diagrams. So this is your complete system, right? Here I am putting controller, which this controller will have input from the observer. This pink part represents the observer. It is estimating the values, and this estimated states are given to K, and then it is given to the input. This is the complete block diagram for the observer. Is it clear? Any doubt? Anything not clear, not understood? It is little bit difficult to understand mathematically, but not that much. If you have any doubt, maybe you can ask me. I will Repeat it. प्रेरणा, काही अडचण, काही डाऊट? आरंभ, अजय, शिवम, पल्लवी, देवेंद्र, राहुल, प्रतीक, प्रतीक लाड, समजलं का? सृष्टी पवार, so this is the concept of observer that I have explained to you. Now this L, which I have shown here, state feedback gain, observer gain matrix. This L, designing this L is nothing but the observer design. When I say observer design, I want to design observer for the system. So in that case, observer design is nothing but the design of the observer gain. So observer design is nothing but design of observer gain L. Design of observer gain L. Earlier we have seen design of state feedback gain. So this is observer gain. This is observer gain. So again, when I say I want to design this, there are three methods. Can anyone tell me what are these three methods? What can be the three methods to design L? What can be the three methods to design this L? Anyone? Umesh? We have already seen the methods to design K. So what can be the methods to design L? Ajay? अरे बोला काहीतरी? Yes, Sanchit has given the answer. Matrix transformation. Then Ackermann's formula, and then direct substitution. Methods are same. The names of all the three methods is same. Whatever we have used for designing K, all the three methods are applicable here. Matrix transformation, Ackermann's formula, direct substitution, all these methods are used to design the value of K. Now, when we are designing the value of K, we say that necessary and sufficient condition. What is necessary and sufficient condition? What is necessary and sufficient condition here when we are designing K? Yes. What is system should be controllable, correct? Omkar, system should be controllable. Now, when I am designing L, what should be the necessary and sufficient condition here? जर का इथे मी म्हणत असेल की system should be controllable, then here for designing L, what should I say? System should be observable, correct? Sakshi, correct. System should be observable. System should be observable. system should be observable. So K system should be controllable. For L system should be observable. काही ठिकाणी L म्हटलंय, काही ठिकाणी KE म्हटलंय, काही ठिकाणी KO म्हटलंय. असं वेगवेगळ्या पुस्तकांमध्ये वेगवेगळं नाव आहे. But here we are using L. System should be observable. Here system should be controllable. Right? And here also we need some poles, locations where we can place our observer poles. So P1, P2 up to Pn. And all the three methods are similar. आता मी तुम्हाला मागे पण सांगितलं होतं की principle of duality x dot is equal to ax plus bu, y is equal to cx. If I want to write a dual system of this, then it will be z dot is equal to a transpose z plus c transpose इथे काय येईल u. आता u च्या ऐवजी आपण त्याला काय म्हणू, v म्हणू. v and eta is equal to b transpose z. This is a dual system, dual, dual system. That means if system, याला आपण system 1 म्हणू, याला system 2 म्हणू. If system 1 is controllable, then system 2 is observable. If system 1 is observable, then system 2 is controllable. If state feedback is designed for the system 1, then it will be a state of observer gain for system 2. And if observer gain is designed for system 1, then it will be a state feedback for 2. This is called as the duality, principle of duality. Right. So whatever methods we have seen for designing K for state feedback control, all these methods are same, only the notations are different, representations are different. इथे काय म्हणू आपण, AB is controllable. Here it will be A transpose and B transpose will be observable. Here AC is observable, then here A transpose C transpose is controllable. A transpose C transpose is controllable, and that is what is used here. So we will just go through that and we'll see how we can do. Okay, so here this is your observer. Okay, so the closed loop poles of any completely state controllable system can be placed at any desired location by the state feedback control u is equal to kx or minus kx. Thus, it is essential to have all the state variables available at any time t to constitute the control law. So this x should be available at any time. Then only we can get kx. If x is not available, then we will not be able to get k. We will not be able to get u. However, in practice, all the state variables are not available for the measurement and feedback. In such a cases, it is needed to estimate unavailable state variables. The estimation of such a state variables is called as observation. Estimation of the unavailable states is called as the observation. And the system algorithm that estimates these variables is known as state observer. State observer. So types of observers we have seen: full order observer, minimum order observer, or reduced order observer. Now I will not go in that. So theory of full state observer. So we have x dot is equal to ax plus bu, y is equal to cx. This is what we have. X tilde, here instead of cap they have written tilde. X tilde can be the state to be observed, which is approximated by the model. X tilde dot is equal to ax tilde plus bu plus ke. Here it is represented as ke instead of L. Here it is represented as ke. Y minus cx tilde, where ke is the observer gain matrix. And this is what is the complete सिस्टम, ऑब्झर्वर सिस्टम, इथे तुम्हाला जी दाखवली मी, दिस इज द सेम सिस्टम. के दाखवलेला नाहीये त्यांनी, बट इट इज सेम सिस्टम. It is same system. So from the above block diagram, we can get the observer equation as x dot minus x tilde dot is equal to ax minus ax tilde minus ke cx cx dot, tilde. So we get a minus kec, a minus kec. आपल्या याच्यात आपण l दाखवलेला आहे, इथे l दाखवलाय आपण, a minus lc, a minus lc, इथे दाखवलं a minus kec. Thus, the dynamic behavior of the observer gain can be determined by the eigenvalues of A minus KEC, and the state estimation with the desired observer gain dynamics can be done by determining the observer gain matrix KE. Okay, so necessary and sufficient condition for the state observer is that system should be completely state observable. Here it is delay. System should be completely state observable. Then only we can design the observer. System should be completely state observable, then only we can design the observer. So design of full order observer, design of full order state observer for desired observer error dynamics involve determining the observer gain matrix. So these are the three methods: matrix transformation, Ackermann's formula, and direct substitution. All these three methods are there. Same methods, and these methods are similar in steps as well. So here first one is computation of the observer gain matrix by transformation matrix method. What is that transformation matrix method? I will not go in that detail now. You can see all these steps and you can solve numericals on that. Numericals are also given here. So first step is that check the complete state controllability, whether the system is controllable or not. Sorry, not controllable, observable. Check the complete state observability of the system. If the system is completely state observable, then the step 2 to 5 are performed. 2 to 5 if it is observable, and if it is not observable, we cannot determine or we cannot have observer for the system, right? So observer is required. System should be observable. System should be observable. So first of all, check observability and then go ahead. After that, once the system is observable, you can obtain the open loop characteristic equation. Then you can obtain the desired characteristic equation, and then determine the transformation matrix Q is equal to Wn transpose inverse. हा एक मॅट्रिक्स कॅल्क्युलेट करायचा, ट्रान्सफॉर्मेशन मॅट्रिक्स Q is equal to Wn transpose inverse. What is W? W is given here. W is given here. From the coefficients of the open loop characteristic equation, you can write down this W. आणि N is, what is this matrix? हा सांगता येईल का कोणाला मॅट्रिक्स काय आहे? What is this matrix? Can anyone tell me what this matrix is? C transpose, A transpose, C transpose, A transpose square, C transpose. What is this matrix? याला काय म्हणतात? याला काय म्हणतो आपण? Observability matrix. So this is observability matrix. So W into N transpose into inverse, त्या सगळ्यांचा inverse, which will provide us Q, and then this Q is written here to determine K. K is equal to Q into alpha n minus an, alpha n minus 1 minus an minus 1, and likewise up to alpha 1 minus a1. If the system is in the observable canonical form, then Q is equal to I. If the system is in the observable canonical form, then Q is equal to I. Is it clear? Now here one example is given. One example is given. X dot is equal to 0, 1, 0 minus 2, x plus 0 for u, y is equal to 1, 0. And we need to determine the observer gain by matrix transformation method. Observer gain by matrix transformation method. Okay, so observability matrix is here. So first we need to check whether the system is observable or not. N C transpose A transpose C transpose हे सगळं काढल्यानंतर we check the rank of N. Rank of N is 2. System is completely state observable. System is completely state observable. After that, what we have to do? कुठल्या steps follow करायचे? First one is check the observability. That is done. Write down the open loop characteristic equation. Then write down closed loop characteristic equation. Determine W. And आता इथे बघा. Open loop characteristic equation is Si minus A. Determinant of Si minus A. So we get S square plus 2S is equal to 0. So with that, A1 is equal to 2. A2 is equal to 0. A1 is equal to 2 and A2 is equal to 0. Observer error dynamics has a characteristic equation. Now closed loop eigenvalues here minus 8 and minus 8 are given. So it will be S plus 8. S plus 8 is equal to S square plus 16. S plus 64 is equal to 0. So we have alpha 1 is equal to 16 and alpha 2 is equal to 64. Alpha 1 is equal to 16 and alpha 2 is equal to 64. And matrix transformation Q is equal to W N transpose inverse. हा W इथे दिलेला आहे. W is given here. W is given here. From this, W is written as A1001, 1001, and that's an inverse. So we get answer as 0, 1, 1 minus 2. 0, 1, 1 minus 2. And after that, we calculate KE as 14, 36. 14 and 36. Is it clear? Is this clear? समजले का हे? Let me know.
Yes,
if,
sir.
let me know if anything is not clear. I can repeat this. No problem. जर कोणाला काही समजलेलं नसेल तर मला सांगा. I will repeat this once again. You will have to do some practice to write this in the examination. There are some equations and block diagrams. It should be clear when you are writing in the examination. Also, you should be able to solve the simple numericals on this. Here I have taken the example of 2 by 2 system, but there can be 3 by 3 system as well. This is another example which is the same that we have seen in case of state feedback control design. Similar procedure is applied here. Similar procedure is applied here to determine the observer gain. This is third example. Now I will not demonstrate all these examples to you. You can try these examples at home. Okay. Next method is Ackermann's formula. Again, same procedure is used for this as well. So here again check whether the system is completely state observable or not. If the system is completely state observable, then apply Ackermann's formula. After that, determine the characteristic equation for a given observer. Whatever eigenvalues you are given for designing the observer gain matrix, from that constitute your closed loop characteristic equation as s raised to n plus alpha 1, s raised to n minus 1 plus alpha up to alpha n minus 1 n plus alpha n is equal to 0. Like this. Like this, you constitute your equation. Then determine the phi a. Phi a is given here. Phi a is what? Phi a is a raised to n plus alpha 1 a raised to n minus 1 plus up to alpha n minus 1 a plus alpha n I. It is the same formula that we have used for designing state feedback control. This is called as Ackermann's formula. Every matrix satisfies its own characteristic equation. This is Ackermann's formula. And from that, we need to determine Ke as phi of A multiplied by observability matrix inverse multiplied by a column matrix. Multiplied by the column matrix. And in case of the state feedback control design, it was exactly opposite to this. It was having a row matrix, inverse of the controllability matrix, and then phi of A. Here it is exactly opposite. Same procedure is followed here. So x dot is equal to 0, 1, 0 minus 2, x plus 0, 4, u, y is equal to 1, 0. This is the system. S is equal to minus 8, minus 8. It is the same example that we have seen just now. So what we are doing is, first we are checking whether the system is observable or not. Once it is checked, we say that system is observable. After that, we obtain the characteristic equation, desired characteristic equation, then matrix characteristic equation. By substituting A instead of S, we can get this characteristic equation. Solve it. That is your phi A. So Ke is equal to phi A multiplied by inverse of observability matrix multiplied by a column matrix. A column matrix, and you get the same answer as 1436. You get the same answer as 14. Look at here, only one page calculations are there, but you need to follow the steps exactly. This is very simple, but it can be asked for the 8 to 10 marks. So if you solve this perfectly, you will get full marks. So you need to understand the steps of matrix transformation method, Ackermann's formula method, and direct substitution method. All the three methods are dual of each other for the observer design and for the state feedback design. एकदा का तुम्ही state feedback design च्या या तिन्ही methods perfect केल्या, you will be able to solve it for the observer also. तर त्याच्यामुळे खूप कठीण नाहीये, but you need to have some practice. Try to solve all these numericals in the notebook. Try to solve all these numericals in your notebook so that you will get complete idea about it. So there are some other examples you can see here, and you can try all these examples. If there is any difficulty, maybe you can approach to me. I will explain you it once again. Okay. And last method is computation of the observer gain matrix by direct substitution method. Direct substitution method means we compare the coefficients of the desired characteristic equation and the actual characteristic equation. And by comparing the coefficients, we get some equations, algebraic equations, and we can solve them like simultaneous equations. And then you can get the values of the unknowns. So we have a characteristic equation like this: Si minus A plus KEC, and Ke is taken as K1, K2, Kn. Also, the characteristic equation for the observer can be obtained from the desired eigenvalues, right? So here check whether, first of all, again check whether the system is observable or not. If it is observable, then go ahead. If it is not observable, then you can simply say that observer feedback, observer gain cannot be designed for the system. After that, determine the characteristic equation of the state observer from the desired eigenvalues. Then determine the characteristic equation from the Ke, that is unknowns. Compare the coefficients and get the answer. Again, the same example is shown here: 0, 1, 0 minus 2, x, 0 for u, y is equal to 1, 0. So here what we are doing is, first we are checking observability, system is observable, then go ahead. So Si minus A plus KEC, this is Si minus A plus this is Ke, K1, 2, and this is C. So finally you get S minus K1 minus 1, K2, S plus 2. And then you get the characteristic equation from here. This one, S square plus K1, S plus 2, S plus 2, K1 plus K2. And this is your desired characteristic equation, obtained from minus 8, minus 8. So S square plus 16S plus 64. Now compare the coefficients. S square चे coefficient काय आहे? 1, 1. S चा coefficient इथे 16 आहे, इथे काय होईल? K1 plus 2. आणि इथे S raised to 0 चा coefficient आहे 64, इथे काय होईल? 2K plus K2. 2K, K1 plus K2. So compare these coefficients and you will get K. You can solve it. So this is again only one page solution to the numerical, and you will get the answer. And you will get the answer. So likewise, you can solve all these numericals, and you can clear your doubts if you have. Yes, tell me if anything is not clear, not understood, समजलेलं नाहीये, काही अडचण आहे. This is already shared with you in your Google Classroom. तुम्हाला काही समजलेलं नसेल तर you can unmute yourself and I will repeat that particular point once again. Yes, Prashant, Prathamesh, Rahul, Sakshi, Sanchit, Safal, Siddhant, have you understood? Srushti, Vaibhav, Vaishnavi, type yes or no, or unmute yourself. Yes, tell me any doubt. Vaishnavi, Vrishali, Sandeep, Sumit, Rahul Shinde. Okay, if there is no doubt, then we can say that we have completed our unit number 4. We have finished this unit. All the topics we have covered. All the topics we have covered. And with this, we will stop here. We will not continue for another 1 hour. We will stop here only. If you have any specific doubt, you can ask. Otherwise, we will stop here and we will continue our lecture tomorrow at the same time 9. And we will finish or we will start the unit number 5. आता तुम्हाला काही अडचण असेल तर विचारा, because we have finished unit number 4 and we will continue our learning in the next lecture tomorrow at 9, and then we will start with the unit number 5. कोणाला काही समजलं नसेल तर विचारा, otherwise we will stop here. आरंभ, अहिरे.
Yes, sir.
Any doubt?
No, sir. Sir, any one method can come in the exam, no?
In the examination, there will be a numerical where you will have to solve it by any one method. It will be mentioned. It will be mentioned that solve it by matrix transformation or solve it by direct substitution, like that.
Sahara Sunday.
Okay.
ओके, ठीक आहे, थांबून घेऊ मग आपण. कोणाला काही विचारायचं आहे का? सृष्टी. Okay, then I will end our meeting. Thank you for joining.